Our next talk today on high-frequency GBT corrections is by Natalie Butterfield. Natalie's a postdoc here at the Green Bank Observatory, and she has used Green Bank, the VLA, and ALMA extensively for her work, mainly on high-mass star formation in the center of the galaxy. So she's an expert on galactic center, molecular gas, and star formation, and has had to use these high-frequency GBT corrections through her own work. So take it away, Natalie.
All right, so today I'm going to discuss high frequency GBT corrections. All right, so just to briefly go over some of the GBT telescope optics. So the GBT has a 110 meter by 100 meter dish, which is part of a 208 meter parent parabola. And so that is the figure that's shown here on the right. So you can see where the dish structure of the GBT is relative to the parent virtual parabola. So the effective diameter of the GBT is 100 meters, and it has a off-axis, clear, unblocked aperture, which results in low side lobes and high dynamic range imaging. All right, so one of the key features of the GBT is that it has an active surface. So with some other radio telescopes like the VLA, you have just a fixed dish, whereas with the GBT, we have 2,209 actuators. And so what these actuators are at the corner points of each block on the dish surface. So these actuators will push or pull, correcting the dish surface to make the best RMS for imaging at the high frequency observations. So with the GBT down in the bottom corner, I have listed different radio telescopes along with the surface RMS over the diameter, just to show how the GBT compares with other radio telescopes that are online. So as you can see, the GBT is comparable to that of ALMA and several other radio telescopes. And so this makes the GBT the largest single dish operating efficiently at 3 millimeters in the world. All right, so we went through some improvements to the active surface back in 2009. And so what the images on the top are showing are just scans of the dish surface over several months. And so as you can see in January 2009, you see a lot of really bright points and really dark points, and that's just showing some deformations that you have in the dish structure. But if you're looking at September in 2009, you see that the dish surface is relatively smooth compared to that in January. And so this is just showing how the improvements to the active surface really can affect the RMS that you're measuring across the dish structure. And then just on the bottom, it just kind of shows a comparison of what the 11.7 gigahertz beam pattern looks like for these different types of dish smoothness. All right, so the GBT achieves its theoretical beam at 110 gigahertz. All right, so this is all described in a memo back in several years ago. So the memo number is 296. And so this just demonstrates the success of the pointing and control system. So the two figures that are shown here are the GBT theoretical beam at X band, which is 9 gigahertz, and then at Argus, which is at 110 gigahertz or so. And so as you can see, the theoretical beam really matches what we're measuring with these two receivers. So the memo also covers some of the gravitational and thermal modeling with the active surface corrections. So you can get some deformations based on just either heat. So say, for example, if you're switching from daytime to nighttime observing, the heat deformations can cause changes in the dish structure. And then the same with gravity. So if you're pointing lower towards the horizon, that can cause deformations in the dish structure. And so I'll cover those in a little bit more detail later on in this talk. But this has just been put through with a lot of work by many people over the last decade. All right, so a surface with random large errors. So basically what this figure is showing on the left is the receiver response, and then compared to on the right is the surface errors. And so the figure on the right is pretty much what you will see when you go through and do your auto-OOF corrections, and I will show those and discuss those later on in this talk. But this is really just showing what the dish surface looks like and where you're seeing just different changes in the dish structure. All right, so model surface using Zernike polynomials. So when you're going through and doing your auto-OOF corrections, really what you're measuring is different Zernike polynomials for the dish structure. So most of the ones that we will be using in the auto-OOF and that you will see later on are Zernike polynomials 3, 4, and 5. Those are usually the most common that we'll be using on there, but the Zernike polynomials covers a wide range of different values. And so these are just some of the different values that you can see here, along with how those translate to the dish structure. All right, so a little bit more on the Zernike gravity model. So each Zernike polynomial is fitted with a function of elevation. And so that's what these polynomials are shown here. If you can see my cursor, so you have an sine of the elevation, bn sine of the elevation. And so each of these different polynomials can have a different value. And so the updated 2014 gravity model improved the telescope performance. And so those different model improvements are listed in this memo, which you can be found here. So that is the PTCS number 76.
So Natalie, we do have one question. What is the difference between the A polynomial and the B polynomial in this model?
Did they give a slide on?
I think the next slide, this slide here.
That is a good question.
Just a coefficient.
Yeah, Dave?
It's just a coefficient. The A coefficients are multiplied by the sine of elevation, and the B coefficients are multiplied by the...
Aha.
Hold it, there's a cosine. There's a typo, I'm sorry. In this, one of that should be either in front of the sine or the A or the B. One's a cosine and one's a sine. That's a mistake in an old slide. That's
okay.
A typo. I apologize to everybody, including Natalie, who, so that should be a sign there. And one of them's a sign. I forget if the ones in front of the A are the sign or the B is the sign, but one of those should be a cosine, excuse me. So.
Okay. Yeah, I can look through that and then post in the chat later on today what the full equation is, or send her on the slide. So, all right, thanks, Steve. All right, so the surface improvements with the Zernike gravity model. All right, so basically the figure that's up in the top left is just showing the changes to the efficiency over different elevations. And so as you can see with the different, like on the bottom, the dotted line is from 2003, and then we go up to 2009, and that was when I discussed the changes to the surface improvements. I showed that figure where we compared January 2009 to September 2009, and we saw how the dish improved over those months. And so this is kind of just showing what the relative efficiency is for those. And then the last one is from 2014, that's at the very top. And you can really just see how well the surface has improved by including these Zernike models and these auto OOFs in order to get the best dish surface possible. And so that is really what this figure is just showing, is how it has changed over the years and how we've been trying to improve the best efficiency we can get with the GBT. So improvements to the Zernike gravity model in 2014 basically resulted in this flat gain curve with elevation and has significantly improved the GBT performance at high frequency. So if you're interested in seeing some of the changes that we've done since 2014, please see memo number 301. All right, and then I guess the figures over here on the right are just showing a similar effect, but at higher frequency. So the top panel is showing what the efficiency is at 80 gigahertz. And so as you can see that the improvements to the dish surface has also improved what the efficiency is at these higher frequencies as well. All right, so surface improvements with the Zernike gravity model. So here, some of the Zernike parameters depend strongly on the current thermal conditions of the antenna. And so those will require real-time corrections to the gravity model. So what this means is that, like I was mentioning earlier, if you're going from daytime to nighttime observing and the air temperature cools off and so the dish surface relaxes, those can change what the surface looks like for the GBT. And so that's what it means by having current thermal conditions or having real-time corrections for gravity. It really depends on what you're looking or where you're pointed at and how those deformations need to be up to date. And so that is one of the reasons why if you're doing auto OOF or if you're observing, you really need to have those auto OOF corrections pretty frequently in your observations because they can change relatively quickly. And I will get at the very end of my talk, I will go over some of the future improvements that we're planning on doing with the GBT. Okay, so some surface improvements with the Zernike gravity model. So the use of the out of focus, so that was the OOF that I was mentioning earlier. So mapping observations of a bright point source to derive Zernike parameters. Okay, so basically in order to do an auto OOF, you really need to have a bright source in order to calibrate your Zernike polynomials. So if you have a fainter source, you really won't get good OOF solutions. And so you really want to use a brighter source in order to do your auto OOF observations. And so the figures here just show what the in focus versus out of focus, either plus or minus out of focus looks like for this source. All right, so an example of the Argus out of OOF observations. All right, so basically the next few slides I'm going to be walking through an example of an auto OOF using Argus. All right, so the first two scans, now that you guys are a bit more familiar with Astrid, so the figure that we have here on the left is the first scan, the figure that's on the right is the second scan, so you can kind of see that listed across the top where you have your list of scans. All right, so the first scan that we're doing shows you what the vein cal looks like, and then the second scan is on the sky. And so what you can see is how the number of counts, so on your graph figure that you have here, so your counts is going to be your y-axis. So you can see how your counts change between looking at the vein versus looking at the sky. And so for a good system, so using these two observations, you can calculate what the system temperature is. And so to do this, basically you take your signal that you have for your sky and you divide it by this vein minus the sky. And so for these observations right here, this yields a system temperature of about 104 Kelvin for a warm temperature of about 270 Kelvin. And so if you have, like in very good conditions, what you expect your values to be is your vane to be roughly 3 times what the sky is under good conditions. All right, so that's the first 2 scans. And then the next 3 scans that you'll be doing are your Argus OOF maps. So an Argus OOF, or an OOF in general, will take 3 mapping scans. So this is what the first mapping scan will look like. So the first map uses the default focus. And so again, you want your source to be very bright so that you have good signal to noise. And then as you can see, the source is offset from the center of the time map. So basically when it scans over your source. And so it implies a significance that you're higher in elevation than where your source is actually located. So basically it's just doing a pointing solution. Then your next one, so the counts are lower since the map was made out of focus. So as you can see between these two, you have really good signal to noise, whereas in here, your signal to noise is a little bit poorer. And then in your third map, so the third OOF map with focus at minus 12 millimeters, peaks higher than the plus 12 millimeter map. So the focus of the LFC will be negative. All right, so this is basically what your 3 maps will look like. You make 3 maps using your OOFs, and then you will be able to solve for your Zernike polynomials. All right, so you go through, you do your 3 maps, and then the system will calculate the 3 different Zernike polynomials. And so once your OOF has finished, you will see a screen that looks like this in Astrid. All right, so just to kind of go over the different parts of the screen here. So the map that you're seeing is basically showing you what the dish looks like at the current Zernike polynomial that you have selected. And so you know which Zernike solution that you have currently selected by looking at the top of the right panel here. So you have Zernike solutions, and then you see Z3, Z4, Z5. And so for these, or for in this case, pretty much it's showing just the Z5 solutions. And so that is what the map is showing here on the right, on the left. And so if you select a different Zernike solution here on the right, it will yield a different map for that Zernike solution. Okay, and so once you've gone through and you've looked at your different solutions and you've checked to see what the surface RMS is for each of your different solutions, and so the surface RMS is shown down here at the bottom of the map. So you'll see in this case, the surface RMS is 136 microns. And so you want to check to see what the surface RMS looks like for each one of your different solutions. All right, so then once you're happy with the solution that you've selected, then you want to click the send solutions with point and focus corrections, and it will send those corrections to the GBT and turn on the thermal Zernikes. So the default that whenever you do an auto OOF, the first one that always pops up is Z5. But you can click on any one of the other Zernike solutions to see what those look like. And just a word of wisdom, so you want to be careful of any RMS solutions that have an RMS of larger than about 350 microns. And so this can happen if it's very windy or other issues with observing. And I'll get into a little bit later what different solutions will look like. Okay, so one of the other things, just to go back, so you have your different Zernike polynomials, Z2 through Z6. So then you can also click on the raw data or the fitted beam map. And so this is what the raw data will look like if you click on that solution. And so pretty much you'll see the different maps that we showed in the scans 3 through 5. So it will yield what those different maps look like. And then at the very bottom, you will see basically what the fitted beams will look like. And if you selected that one on the side, it will also show you all of the different fitted beams for the different Zernike solutions. All right, so then, so then if you click on the fitted beam map, it's going to show you what all of the different solutions will look like for the different Zernike polynomials. And so the let's see, Z through 3 through 5 are the bottom 9 images that are shown here, with Z3 being the top panel, Z4 being the middle panel, and Z5 being the bottom panel. And so you can see how the fitted beam maps will change slightly for the different Zernike polynomials. And so this is the best case scenario, or one of the better case scenarios. If you have poor OOF solutions, then a lot of these maps will look different, where sometimes you'll get some molted images. So using the fitted beam maps can be a nice way just to see how they vary across the different Zernike solutions. So that's what these different selection options are up here, where you can see what the different maps look like for your different solutions. Okay, all right, so the auto OOF example solutions. All right, so these example solutions here basically show what your surface structure can look like for different solutions. All right, and so on the left, we have one of the better auto OOF solutions, where you see very shallow variations across the dish structure. There's not really a whole lot of sharp changes, whereas on the right, you see some very high points and some very low points. And so measuring what the surface RMS is for this one that's on the right shows an RMS of about 626 microns, whereas the one on the left shows a surface RMS of about 200. And so anything that has a surface RMS of less than about 400 microns is usually an acceptable result. If you start to see anything that has these large surface variations, or you see a very large RMS, that's usually an unacceptable OOF solution, and you wouldn't want to apply it. And so just some of the raw data streams. All right, so this is one of the ones that I was mentioning earlier. So how if you have a poor OOF solution, or if your source is relatively faint. So in the case of the panels here on the right, your fitted beam maps will look like this molted type of structure, and you really won't get these strong signals that you see in the source on the left here. So the source on the left is what it should look like if you have a good solution. If you see something on the right, it's usually the sign of a poor solution, and you might need to find a brighter source to do your auto OOF. All right, so here's another example of a bad auto OOF solution. So in this case, the observations were done through the keyhole. So that's basically when the telescope is pointed straight up. And so the OOF RMS is 438 microns. And these have a large implied focus and pointing offset. And so you can just see here that you have these large deformations near the edge of the dish. And so this is kind of an example of what a poor auto OOF solution will look like. All right, so then if you check the fitted beam maps, you get these sort of smearing type patterns. You don't really get nice point sources. And so this is just an example of what your beam solutions will look like if you use these types of observations. So you want your beams to look relatively circular. You want them to look as nice as possible. And so this is just an example of what a bad auto-OOF solution will look like. So you want the observed beams to not look like streaks or elongated. And again, this is something that can happen in windy conditions. And so you don't want to apply or send OOF corrections if you don't trust the results. So just because you take an OOF solution doesn't mean that you have to send it. If the solutions don't look great, then you don't want to send those corrections to the GBT. All right, just another example of a bad auto-OOF. So in this case, if you're looking at the Z3 fit, you see these large streak patterns. And so this is the type of thing that you want to keep an eye out for and avoid when you're looking at your fitted beam maps. So if you see something like that, then you don't want to use that solution. All right, so the Clio status window. So your as and L pointing corrections. So this just basically shows you where those corrections should show up. And then you have your focus corrections, and again, it shows you where they should show up. If the corrections or heuristics fail, then you can manually send those in, or you can relax heuristics, which I'll show later. But this is where you want to check and make sure that your corrections have been sent to the GBT. So the active surface, you want that to be shown as on with thermal corrections from the auto-OOF. And so those are what should be shown here. And then your Vegas balance values on the sky should be roughly 20. Sometimes they can be a negative 20. They sometimes can be a little bit higher than that, sometimes a little bit lower than that. But if you see something that's 30 or anything like that, then you want to check to make sure that those values are okay. But they should be about negative 20. All right, so just briefly some observing strategies for the antenna optimization. So you want to make sure that if you're observing at high frequencies, that you point and focus, which is the auto peak focus, every 30 to 50 minutes, depending on conditions. So the point and focus roughly takes about 5 minutes. They're each about 30 seconds to a minute. And so sometimes it will take some jump time. So roughly you want to include about 5 minutes of overtime every 30 minutes in your initial setup. The auto-OOF, which takes about 20 minutes. Each of the map scans that I showed earlier, so you have to take 3. So each of those are a little over 5 minutes a piece. And then you want to give yourself time to look over the solutions and then be able to send those solutions to the GBT. So you want to make sure that you estimate about 20 minutes to do an OOF and that you use the correct, to correct for the surface and the thermal effects at night. All right, so some daytime surface changes. So about every, or a little under every hour, time scales, and you want to make sure that the auto-OOF solutions are correct, as they can cause more harm than good for rapidly changing conditions from the auto-OOF. And so this is typically, if you're observing during the daytime, you can run into some of these quickly changing conditions. And so I'm going to get into a little bit later some of the future things that we're working on to correct for that. So it is typically not useful to use the thermal corrections during the day. Okay. All right, so as I mentioned earlier, so it is important for high frequency pointing and focus observations, so anything that's above about 20 gigahertz or so, that you select the heuristics to be relaxed. So to do this, you would do this in Astrid. you'd want to click on Tools at the very top and then go down to Options, and it will show a screen that looks like this. You want to click over till you get to the Heuristics tab, and you want to make sure that the Heuristics is relaxed. All right, so this is going to be my last slide, but just to wrap up kind of some of the future things that we're working on. So there is a accepted proposal that is called LASSI, which is a laser scanner, which is shown here in this figure, just as a diagram of what LASSI will be doing. So LASSI is going to be situated up near the receiver cabin, and it will be scanning the dish periodically and basically be able to detect the different or subtle changes in the dish structure, and then be able to send those to the control room or send those to the GBT and be able to make real-time changes to the dish structure, and hopefully cut down on the time that's needed for the high frequency auto OOF procedures, and to be allowed for more daytime observing where you get quick changes in the dish structure. And so if you have a scanner that's able to scan the dish, then you'll be able to correct for those changes real time. All right, and I think I'm out of time, so I will stop there and then take any questions.
Thank you very much, Natalie. For anyone who would like some hands-on time with Argus or some more in-depth explanation of some of the techniques that Natalie talked about, David Freyer has offered to give some supplemental instructions tomorrow at some point. So if you're interested in that, please send Dave a message on here or send me a message and I can put you in contact with him.
Hey, Will, and thanks, Natalie, for presenting. I'm just going to jump in and recommend, like when we're doing the high frequency auto OOFs and stuff, we can use the instrument like Argus or Mustang to do it. But I would, if the KA band receiver is up there with the Caltech Continuum back in, you get much higher signal to noise with the OOF solution. So I would recommend using KA to do your OOF and drive the surface corrections that you use for your Argus observations. We found that works better. And another advantage of the lower frequency to derive the surface corrections is the fact that the beam is much bigger. So if there is a little bit of wind jiggling your beam around, you don't see it at KA band, and you can, but you will see it at Argus, and you don't want to try to correct the surface to correct for effectively the winds, which look like a smeared source. So at Argus, so you can actually get a bad solution with Argus and low winds, where you would get an excellent solution with the KA and low winds. And the other advantage is the sources are much brighter at KA, and you get much higher signal noise because the Caltech back end is a fast switching, it's designed for doing good continuum work. So the signal noise is 20 to 100 times higher. But the KA band receiver is not always up. If the KA band receiver is not up, then you have to do Argus if you're doing the Argus observation. And then you just pick the brightest point source in the sky. There's only a half a dozen of them that are pretty good to use at Argus, where you could do 30 or 40 sources at KA. That would be plenty bright.
And Natalie, you mentioned at the end there, the LASSI project. Do you want to say something about LASSI, how it will interact with Argus in the future, or with OOF in the future?
Yeah, so I think that might be a question for Pedro. I'm not quite sure how the two systems will talk to each other or what type of information it will fully send. But Pedro, since he's the postdoc who is working on the Lassie project. He might have a better answer for that than I would.
Okay. Yeah, I think right now there's no Lassie integration into high frequency observing, but there could be some integration. I think next summer there will be some commissioning, some more commissioning of it.
It's demonstration commissioning through August 2021.
Okay.
And then another project will have to ensue to actually move Lassie into a usable instrument hooked in with all the other systems on the GBT. So it's probably fall of 2022 at the earliest before it would be able to be used with observations.
Any final questions for Natalie? If not, thank you very much.